You are listening to EE Times on Air, and this is EE Times Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Dr. Patty Stabile talks about creating optoelectronic neural networks. Your hosts are Dr. Sunny Baines of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Baines.
In today's episode, Sunny is talking about photonics in neuromorphic engineering with Dr. Patty Stabile from Eindhoven University of Technology in the Netherlands. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Patty's team has achieved optical neural networks enabling ultra-low-latency processing. The semiconductor optical amplifiers in her system don't just compute, they compress noise and regenerate signals, preserving accuracy at scale. Looking ahead, Patty predicts optical neuromorphic computing products within 5 years. There are links to her work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. Patty Stabile, welcome to Brains and Machines.
Thanks, Sunny, for having me here. Thanks.
Let's start with your background. What did you study and what led you to get involved with neuromorphic engineering?
It's a long path to there. Actually, I'm an electronic engineer and I did a PhD in nanoscience, so nanotechnologies. But then I went here, actually, at Technical University of Eindhoven, where I started working on large-scale photonic integrated circuits for optical switches for data centers. By then, I had also contact with people from MIT. I also went there for 1 month to visit them. And it was just an intuition that let me think that I already had chips which could run some sort of processing, neuromorphic processing. And that is why I decided to move into this new research challenge of neuromorphic engineering.
Okay, fantastic. Let's start with the basics because you are the first guest that we've had on the podcast who specializes in working with photonics. So there is a rule of thumb that bosons, which is what photons are great for communication because they don't interact with each other. That's why we use them in fiber optics and so on. And fermions or electrons are great for computing because they do interact with each other. And in a way, the neural photonics that we talk about often go against this rule. Can you explain why it's time for us to rethink that?
Yes, these assumptions are correct, indeed. The photons do not interact very well. That's why they are very good for optical communication. And they're also hard to store, so you may tell me, why to use them for computation? However, they can allow a huge parallelism, so they can multiply the amount of data that you can send in and that you can process at the same time. And they can also be ultra fast, very fast, so they can guarantee computation in a very short period of time. So I think these are the two main reasons to think if it has a sense and to experiment that and to show that, to validate that actually they can be both at communication and also at computation.
Okay,
yes.
We'll get into the details of how that's done a little bit later on. But first, can you talk about wavelength division multiplexing, which a lot of people won't be aware of if they come from an electronics background? Just explain what it is and how it fits into the neuromorphic architecture that you've been working on.
It connects a bit to what you just said, the fact that since the photons do not interact very easily each other, WDM, so wavelength division multiplexing technique, send in multiple signals in one single fiber using different colors. So you can send in multiple colors into one single fiber, and that will multiply the throughput, the amount of information that you send in your chip. So that is one of the main reasons why it has a sense to move to photonics and to think about photonics for computation. The fact that you can multiply and parallelize the number of operations that you execute at the same time.
Right. And also important to note that the kind of waveguides we're talking about, they don't have to be fibers that are spun out separately. They can also be built onto a chip, right?
Indeed, it's what we do. We do realize these photonic integrated circuits that have some sort of miniaturized fiber, but on a chip. And in that case, you call it waveguide. So you need to couple the fiber light into these photonic waveguides on chip. And also we use WDM in our implementation because indeed we have multiple inputs. So we have a spatial domain. So we have multiple interconnectivity. And for each of these incoming waveguides, you can send in multiple colors. So you have a spatial domain, a color domain. So you can play with these optical domains to multiply the amount of information that you send in at the same time.
Right. So it's getting around the problem that we have that you can only send one signal down a wire, at least at once. Of course, there is time multiplexing, which we often do in electronics.
Yes, we can also do that in photonics.
Why don't you talk a little bit about the architecture and how the WDM is used, how it goes from layer to layer, so that we can get a sense of what it looks like?
Yeah, so there are different ways to do at the moment photonic neural networks on chip by using different architectures. Generally, people use a basic neural model, McCulloch-bit model, which is really basic. So it has a linear part and a nonlinear part. A linear part, which is practically including algebraic operation like multiplication and accumulations. That is also called the synaptic part, is linear part. The other part is a nonlinear operation. It's a kind of a thresholding function. When you get to a certain threshold, your data, you pass your information or you don't pass it. So that is the starting point. Then each of us can choose which photonic components works better, save more energy, and is faster or is fastly programmable. What we use, actually we use amplifiers. But because we here in Eindhoven, we have these clean rooms and the state-of-the-art clean room on indium phosphide. And therefore we can co-integrate on chip both the laser sources, the photodetectors, but also semiconductor optical amplifier, which allow you to amplify the signal. And we use these amplifiers to realize both the linear operation and the nonlinear operation. In that way, we realize chips which are always including arrays of amplifiers. We keep using the same devices, and therefore we can also improve the fabrication yield. Yeah.
Okay, great. So forgive me if I get this wrong, but my understanding is that at the moment, the way you do it is that essentially the photonics is implementing the interconnections and the synapses between layers, but then the neuron is itself implemented electronically.
No, actually, we implement all optically, in the sense we implement the neuron and the layer of neurons and the connection between layers of neurons all optically. So we realize the neurons or the synaptic operation of arrays with amplifiers that then we combine with optical combiners. Then we realize the nonlinear function with semiconductor optical amplifiers again, but operated in a nonlinear regime. Then we come out with an optical input, which is then, again, injected together with the other outputs of the first layer, injected into the second layer in an optical fashion again. So we never move into the electrical domain, and that allows us to keep running the operation at ultra-low latency without asking memory to give us data or to process data in the meantime.
That's great. You've moved on a bit from the last paper I read, where I know you were planning to do all optical, but I don't think you'd quite got there yet at the point where that paper...
Because we stopped at that time at the first layer implementation, but now we have insight that we can actually arbitrarily stack multiple layers, one after the other one, without moving into the electrical domain.
Okay, great. So before we move on, I want to talk about size. So one of the things about optical photonic circuits is that they're much bigger than electronic circuits. And obviously you're not doing them in 2 nanometer processes because your wavelength of light is hundreds of nanometers. Can you talk about that and why that doesn't bother you? Why that's not a problem for photonics? And we'll get later into also what are the applications? Why should we care about doing all of this at the speed of light?
This is a really great question. A lot depends on how you plan to interface optics to electronics. As long as you integrate them in a planar way, so you have, electronics, then a photonic chip, and then the electronics again, that doesn't really bother much because eventually you don't have to match the size of a photonic waveguide with an electronic transistor. But at the moment when you try to stack in a 3D, or you do a monolithic, let's say, a 3D integration of the optics and photonics, then size matters. So that is not something that we are trying to do at the moment. And of course, to do the vertical stack, you need to move into the nanophotonics and try to miniaturize even more. So what we are doing at the moment, we are using indium phosphide, which has size which are even larger than the one that you would realize on silicon photonics. But I can already anticipate it here, for example, in Eindhoven, we are also playing with the new technologies like membrane in indium phosphide, which allows to realize more miniaturized chip at the same size as a silicon photonics chip. So there is research in that sense to try to reduce and to move into the nanophotonics also in a sort of an active platform like indium phosphide, but it's still, at a premature phase.
Okay, great. So one of the things I've wondered about is why you would go towards having optical neurons at all. I remember some of the very early optical photonic neuromorphic work done at Princeton. And actually, I used to cover optical computing back in the 90s. And one of the advantages of optics has always been in its ability to route very fast, very efficiently, without heat. Why aren't you just focusing on the communication side, which has always been optics' strength? What is the advantage of going into this all-optical network? And what are the applications that you might be aiming at?
The reason is that since it's very good in communication, we can exploit the ultra-low latency of passing the information from the input of the first layer to the output of the very last layer. So in that sense, I would think about communication. So communication between the different computing parts still in the optical domain, and so to have ultra-low latency computing. And by the way, the idea of Princeton was really one of the very first one and super great. So I really appreciate that idea. And in that case, they suggested to use like electro-optical nonlinearities because indeed they are stronger. There may be some problem with the speed in the conversions, but I think that is also a very great idea. But yeah, the point is indeed to have an ultra-fast communication between all these computation units. So that would be really a computation, and the unique essence would be really the combination of communication and computing all in the optical domain. I don't think we think to replace electronics, but the best would be a combination of the two. But we could do a certain number of layers all in the optical domain to help accelerating a number of not only synaptic operation, but really of AI operations that we may need in our computing engines.
That's very interesting. So essentially what you're saying is that the optical neurons would be part of the infrastructure that allows the communication to work better. So
Yes.
You would still be focused on the communication problem within a larger machine, but you might need some intelligence to do the routing or other
Yes.
things within the optical network, and that's why these networks could be important.
Yeah, also with electronics, it's needed, yes, because we need to reprogram it, and there is some additional intelligence to do that super fast, yes.
Right. So you said that your neurons are implemented using semiconductor optical amplifiers in terms of the nonlinearity. But then there are different ways of implementing those. I know there are ring resonators and various other bits and pieces that can perform these. You talked about nonlinear materials. I remember back in the day when I used to write about holography, we would look at things like lithium niobate and all of these incredibly wonderful slow materials that did amazing things. But as materials, they weren't great in the long run, right? So can you talk about the structures that you think might be promising and maybe have smaller footprints, maybe are more efficient than what you're using at the moment? Or do you think semiconductor optical amplifiers are the way to go?
Yeah, definitely there is power consumption metrics to think about here, also about the size and the data rate, how fast are these nonlinearities. So you need to have a medium which allows for strong linearities, therefore energy efficient, and ultra small. If we are looking at that, I think semiconductor optical amplifier may not be the right way to go, even if, they don't scale really quadratically with the size of the neural network. So in principle, we can live with that. But I like our nonlinearities because it allows to reduce, to compress the noise. In the way it is made, in the way it works, it allows you to regenerate the signal and at the same time to compress the noise so that you guarantee scalability, but at the same time also high accuracy by the end of your network. And that is something that we cannot leave out. So it's not just trivial. So it's really plays an important factor. So I think it's still a very good nonlinearity to be considered. We are doing already research on new materials, which still allows for scalability, therefore for amplification and intrinsic nonlinearities. But the point is to reduce the size from 500 microns to 100 microns and even further. So yes, it has a sense to continue with that research because eventually the point is to reduce the size but improve the energy efficiency. Yes.
My understanding is that in terms of power, which you mentioned earlier, that the raw numbers are kind of not great at first glance for photonic neuromorphic because essentially once you turn on your laser, you're burning a lot of power. But that this is actually misleading because the use of light scales completely differently than the use of electricity to communicate. Can you talk us through that argument?
I don't think the problem are the laser per se, because again, also they don't scale linearly as long as they encode information into your chip. But eventually you need to think about, of course, the end-to-end system, what is that we spend electronically also to switch on all this system, but also how much power you consume for computing. And that's true. If I use amplifiers that are current biased, I spend a lot of energy. If I substitute them with elements as there are, which are like more energy efficient, could be the microring resonators, but could be also the Mach-Zehnder interferometers and other kind of devices, talking about the synaptic operation, I think you have an immediate scaling down of power consumption, which is of order of magnitude. So when we talk about these engines, we always have in mind that we will move in that direction at some point, substituting the synaptic operation that now I have for free in my, say, chip, simply because we are really good at fabricating them and realizing them with high fidelity. But eventually we are going to move into some more energy efficient components that are already used and suggested in many other good works like Princeton and MIT. So there are ways to improve in energy efficiency, and I don't think the biggest problem are the lasers. And also for the nonlinearities, thinking about the new research that we are doing and other people are doing at the same time, I'm sure that we'll also move further also there. We will get great results also there in a few years' time.
So as you've said, you're working with indium phosphide. Silicon tends to overrun everything. We already have a field of silicon photonics. Do you think that will be true here as well? Does silicon support enough nonlinearity in the photonic regime for that to be possible?
I think it supports quite some nonlinearities, but one of the big problems in silicon is, again, the losses which are not balanced by an amplification. So the key point in our platform, apart from, of course, the nonlinearities, is also the fact that we can always make use of amplifiers. Definitely all kinds of hybrid integration technology which are coming out, for example, the HP lab also, they have a great technology platform now, are essential because they will co-integrate amplifiers with all the rest. Now the question is, it is better to co-integrate or hybrid integrate it as single devices, multiple of them to have amplification on chip, or if it is better to think about more a chiplet kind of approach where you have really processing signal that you can couple to the rest of, the silicon photonics, for example. But that has to be, analyzed carefully.
And how do you see these systems getting into the market? I mean, having written about WDM and photonics in the past, I always assume that these things would actually end up being used for full-on communication systems first, before they end up being used in supercomputers like Spinnaker. But I know, on the other hand, that these server-side AIs do need connectivity and maybe would welcome them. So where do you think the first real photonic systems are going to emerge, at least that have some optical neural capability, bearing in mind that optics already exists in major computer systems as a way of transporting signals?
At the moment, the good step that I see is, for example, from NVIDIA, as had been announced last year, they are already trying to integrate optical interconnections to connect the GPUs, multiple of them, to improve connectivity, so to reduce power consumption due to communications, and so on and so forth. So that is a very good step that when optics can do its job will be included, even if there are some operational costs to be added. I think one of the biggest things which has not been yet solved is really the low latency. Things happen, there is a cost to it, and they are not that fast. And the same happened when we also asked ChatGPT to answer to some of our questions. There is always a delay in the time of thinking for simple large language models, So we are not talking about yet application where you really need to react to ultra short time. So I think there is plenty of opportunity there for optical computation. And I think those will be the first markets where optical computation will start taking the lead, or will start entering at least with the first prototypes. Considering that we cannot do huge, ultra-large engines at the moment, those are like autonomous vehicle control, for example, in the RF front end, or DSP, ultra-low-latency DSP, and so on and so forth. So I think those are the kind of markets where we will start seeing optical computation have say, let's say.
Okay. And would you see it at some point as making it into general communications infrastructure, not for AI in particular, but having sort of smart communications based on optically driven AI?
I think so. If we talk about communication, this will easily connect to the also large chunk of research which is done on optical switching, for example, for the optical communication infrastructure. So we do have the digital optical switching. Of course, they are digital, but we could adapt some sort of on-chip intelligence where you can process already your optical signals and route them in a smarter way, let's say. So I think that is an obvious way also to go. And I used to work on optical switching in the past, but we also have colleagues and people working on optical switching. So it's very easy to talk and try to merge these two ideas.
Very good. So how long do you think we have before we start seeing these neurally based optical systems appearing, whether it's in big computer systems or in communications networks?
Again, I think the first market that will be considered will be like small engines for like drones or for autonomous vehicle in general, or air front end. What I think is that the first wave of optical computing has been already passed, and there was a lot of interest. Then it's been a bit going down, but recently in the last year again, this second wave is starting of optical computing.
I think this is the third wave. I was there in the 90s.
It's already the third one. So there was a very first wave. So that was a wave zero. That's why.
Okay, wave zero.
Yeah, okay. But there is a new wave coming in, and I know a lot about a lot of optical computing startup coming out. So this will strengthen the interest and also the efforts put on and the money is put on. And I'm sure that within the next 3-4 years, let's say, by 5 years, we will already see some sort of more realistic product on the market, or at least demonstrators that will really validate the importance of potential optical computing. So that is my feeling.
So you mentioned that you think optics will be very important where you have low latency applications and lightweight applications, as opposed to the big server farms that we've been talking about. Obviously, power is one of the issues there. Latency is critical for drones. Talk us through how that might look architecturally.
Yeah, so I'm thinking about optical sensing that has to be added up on our, co-integrated or interface to our chip. So I assume there will be a lot of optical sensings there that, we can immediately process on the fly on these optical engines that we will realize. So you have the sensory inputs, perhaps multisensory inputs, processing for creating different cluster of informations, and immediate feedback to how the drones should react, avoiding obstacle, going faster or going at that point or whatever. So it's ultra-fast control loop, which starts from the sensing, moves into the optical processing, and gives already an answer that then drives the next action of the drone. That I think will happen ultra-low in an ultra-short period of time. And it has to be done on something which is very light, like a photonic integrated chip or like an integrated chip in general, and ultra-low power consuming. Yeah.
Yeah, so you mentioned, I think you said an order of magnitude, lower power, you thought right out of the box for optical?
I was not comparing with electronics. I was comparing with what we have now. So we have now with our architecture quite some power consumption. We are talking about as energy consumption, we talk about picojoule per operation. But at the moment you move and you improve your synaptic operation, which is the one which spends much more power with respect to nonlinear operation, because it scales quadratically with the size of your network, then I expect to go down 2-3 order of magnitude lower power consumption. So that is something that already other people are doing. So they indeed shows better number because we don't have current-driven devices as we have, but voltage-driven devices. So in that sense, we can be energy efficient and go towards the same efficiency number than you have in electronics. At the moment, we talk about, I think, hundreds of femtojoule per operations, and this is doable, more than doable with photonic components.
Although, of course, it's always difficult to compare until you start getting into end-to-end.
Because we are not talking about the size, we are not talking about the real number of operations, which are really rapid. Yes, that's true.
Patti Stabile, thank you so much for coming on to Brains and Machines.
Thank you, Sunny, again. It was really a pleasure to talk to you and to answer to your questions.
Thank you, Sunny. So it's the first time that I finally hear an expert explaining optical neural networks. I very much enjoyed it. To know more about Patti Stabile, please go to brainsandmachines.net. And now we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hello, guys. Hope you're well. I've got a little bit of frog in my throat, so forgive that, but otherwise, all good.
Ciao, guys. Ciao, Ralph. Sorry to hear that. So let's start with Ralph's impressions, and then we move forward.
Sure. Always loved photonics neural networks. It goes back to the Princeton papers that you referred to, Sandy, as well as I had a mentor, somebody who sat on my PhD, Nabil Farhat from University of Pennsylvania, who was very much into it. But at that time, it was essentially masks that were static. They were just passing right through them and using the transmittability of these masks in order to do some kind of inference. What is really cool these days, I think, is the fact that we're starting to use metamaterials to programmably change the transmittability of these networks and of these masks, basically to be able to implement weights multiplications, weights that can be dynamically changed through learning and so on. So that, I think, for me, is what really this area brings to light. Of course, given the speed and everything else that comes along with photonics. So I'm really keen to see where it all goes.
So for the listeners, WDM is a wavelength division multiplexing, sending multiple signals simultaneously. So each encoded a different color, so the wavelength of light. So one thing that I found interesting is that the communication is efficient without heat, which is super interesting for someone that has worked with neuromorphic digital or analog, specifically analog, because photons don't dissipate heat the way electrons do it in transistor. So one thing that I'd like to talk about, which I'm sorry to, but I want to, is the limitations. So as far as I understood, size, power consumption, reprogrammability, and end-to-end integration or fabrication complexity could be part of the limitation. But what I would like to know from you guys is what is among these the one that is worrying you the worst and why?
I'll start on that. So weirdly, a few years ago, I was writing a different book. So not this book on neuromorphic engineering that Ralph and I are slowly coming to an end of at the moment, but a book on writing about technology. And in that book, I wanted to do a case study. And so I wanted to pick a technical subject that I really loved. So I chose photonic neuromorphic engineering because I love neuromorphic engineering and I love photonics. As part of that, I really looked into what was going on, what were the advantages and what were the disadvantages of photonics. And at the time, the technology was just not ready. The lasers weren't ready. Yes, there was a bit of silicon photonics, which you will still hear about, but it wasn't ready. And the thing is, photonics and neuromorphic engineering is still well behind where we are in neuromorphic engineering generally. But I think it's just one of these things where you just have to wait for that technology curve to catch up with where it becomes useful. Now, the one thing that I wonder is, do we really need fully photonic networks? Or do we, in the first instance, need to start putting photonics into our neuromorphic networks as the kind of communications backbone and maybe have a little bit of neuromorphic in it there? And that was what I was trying to ask Patty when we were discussing.
But then, for example, one of the problems is end-to-end integration, so interfacing the optical chip with electronic. So wouldn't it be even worse than having something smaller and then having to interface?
Well, it depends what you're doing with it, right? The beauty of WDM is you have one wire and you have lots of different signals because, as I was saying or alluding to, sorry if it was a little bit of an insider conversation because I have this photonics background, which is even older than my neuromorphic background. But the point about bosons is you can have light at 532 nanometers and light at 534 nanometers. And those photons will not interfere with each other. They will not bother each other as they're traveling down exactly the same wire, which is how our telecommunications network operates. And you can get dozens or hundreds of different wavelengths all going down the same fiber at the same time. So potentially you have the ability to move from board to board, rack to rack within a big neuromorphic system and not be adding extra time to the propagation of that signal.
So that's essentially one of the things that I worry about, and that is to do with the fact that you have a limited number of different colors, the equivalent of colors that you could send down that one pipe. So doesn't that limit the fan out, if you will? How many neurons you can send signals to if you're assuming that each color is the output of a particular neuron.
You can say that, but if you think about this, the fan out on a WDM signal is massive compared to the fan out in an electrical signal, right? So I was just writing a little section of the book. If we're lucky, we can get 10, maybe 20 actual physical connections coming out in 3D with materials that we don't have settled yet coming out of a neuron. And then you're relying on sparsity after that. You're relying on temporal division TDM. So this is like you've got an extra dimension to work with. So you've got the wavelength division multiplexing, and you can consider each wavelength to be like a separate wire, and there can be dozens or hundreds of those. And then on top of that, you can do your time division multiplexing as well. So potentially in the right kind of circumstances, and especially as I imagine it, connecting boards together or racks together, that could be really huge. And if you need a little bit of neural behavior as you're en passant, through your fibers, then Patty's kind of networks seem interesting.
So what you're arguing is that essentially it's like having N, where N is the number of different colors, if you will, in your channels, right? So you multiply that by the N, but okay, so that's fun. I get that. So it's not that every color represents one neuron output. And also the fact that you're dealing with the optical domain now. So your speed is really high. So you can really multiplex it really fine in the time domain. So that's really cool as well. The one thing that I worry about as well for me is how do you weight the values individually? And I think that's where these other examples of the metamaterials or other approaches comes into play. And if you had a way of saying, hey, new neuron is supposed to be receiving a weight of 25 from neuron n-1 behind you, that stair multiplication is something that you didn't address. And it would be nice to see a little bit more explanation of how that is done.
So the weights are quite straightforward because the weights are just filters, right? So all you need is an optical filter that's going to...
But it has to be dynamic, right? It has to change, it has to update and all that stuff. It's not just sticking a filter in the old ways of doing it.
No, sure, but you can make electronically controlled filters that are nevertheless not slowing down the photons going through it, right?
What I mean by that is that you are only at the limits of the light modulator. So if your light modulation is happening at the electronic speed, but your computation is happening at the photonic speed, then there's a mismatch. 10 to the minus 15 femtoseconds versus picoseconds. So there's at least 3 orders of magnitude difference.
Yeah,
there.
but remember, when you're making electronic neuromorphic neural networks, the time constant of the synapse is not the same as the frequency of the signal that's going through it. So what I would argue is that, yes, you will have some kind of limit in how fast you can change those weights. You're not going to want to change them radically too quickly anyway, right? You're going to want them to be stable or changing at a fair clip, but not at the speed of light. I don't see any argument as to why you need weights that are changing at the speed of light.
So I can make an argument for that. It is not that you're going to interface with the real world. We agree with the real world is slow, so to speak, right? But if I'm pumping tokens, I'm doing an AI computation, in that case, you might want to update the weights as fast as you possibly can, because then that gives you throughput to your system that is going to be way faster. So there is a place for, if you could update weights at the speed of light, people would like it.
Yeah, I don't think that's ever going to happen, though. The problem is that all of the active components that deal with photonics are much bigger, clunkier, slower than you would want them to be. So if you are looking to replace all of those and have them outperform, the way photonics will outperform is only through the speed of light and the fact that it's not interfering with anything, so you can get this amazing fan-in, fan-out property. But you're going to be controlling it with electronics, right? Yeah. That's going to be the best way to do it. And so you're not going to improve the performance of the thing that's controlling the light.
I'd like to steer a little bit the conversation towards something else that is important, right? So we talked about speed, but also power consumption. So the lasers and current-driven amplifiers currently consume a lot of energy, right? But he argues that this is fixable by switching to voltage-driven components. So I want to know what you think and what does that mean exactly?
I didn't quite follow that argument, but there is a big difference in the way we think about power consumption in an electronic network than in a photonic network. And that's simply that you're not energy away as you go in the same way that you do in an electronic network. It's not necessarily that it's de facto each component is more efficient. But if you're using the system right, the system as a whole can be more power efficient.
What I've read as well is that the per capita cost or power per compute that's done actually decreases the larger your network is, right? So it allows you to scale up. In fact, folks that work in this domain want to go bigger because bigger gives them much more power savings. So you're basically investing a non-recurrent cost at the very beginning, and then that cost gets distributed across all the compute that you're trying to do. And the more compute you do, the better off you are. You get more efficiency.
That's exactly the way I understand it, is that it's the opposite of scaling badly. It scales well. And actually, if you look at it in a small scale, it's a disaster. But if you look at it in a large scale, it's potentially very powerful. But that's not to hide the fact that however far forward or back you think neuromorphic engineering is, photonics is definitely further back. Right? Photonics is definitely at least, I'm going to say 10 years behind because they don't have the same level of infrastructure in terms of all of the tools to build stuff, even though we have the telecommunications network and we have the fibers and that kind of thing. The stuff that you need to do to make a photonic neural network work, these things are quite sophisticated.
So one of the things that I've seen a little bit more as well in recently is how to use photonics to make really parallel high bandwidth memories, right? Because the whole thing about acceleration these days is always compute in memory. But then how do you get the memory to be local? How do you get it to be fast and so on? So I think there's a play there as well. Maybe it's not in the compute stage. The compute could still happen in silicon, so to speak, in electronics. But the way that you get access to the data coming from these massive memories holding all the parameters of your network, that can also be hyper accelerated by photonics.
What kind of optical memories are you talking about? I'm really curious now, because as you know, I used to write a lot about holographic memories back in the day.
So it's not that the memory itself is photonic. The memory could be electronic, but how to get access to it and get it in and out.
That's the thing that, although I thought what Patty had to say was really interesting and hopeful, I still am not finding the compelling case for switching away from that idea that photons are for comms and electrons are for compute. And I used to be really involved with the whole optical computing community. And most of optical computing was really not optical computing. Most of it was optical communications within computing. And I remember there was a guy, David A.B. Miller from Stanford, Scottish guy actually, and he would say, you know, you can fit your brain in a pizza box, and he would talk about the number of synapses, and he would talk about the RC problem with wiring and all of that stuff as part of his pitch for optical interconnects within computers. And I still find that a compelling argument. I still think that's coming. And in fact, I know it's not just coming, it exists. I know that, for instance, Cerebras, when I went to visit them a few years ago, I know they were looking at optical interconnects to connect their giant platter-sized chips, you know, these things that were bigger than your laptop practically, as I recall. They were amazing. But of course, you're going to use light for communication. And it's just how sophisticated can you be in the way that you use that light? And if you could put even just a small number of neurons in that data path, that communications path, that could be amazing.
Yeah, and you can reuse it.
Also, Lumai, which is a very young startup in Oxford. I talked with the CEO a while ago now, but they're doing very good stuff. And also on the positive side, I'd like to mention some applications that I found. So I saw some papers in Nature directly, 2025, and Nature Communications. The first one is integrated photonic neural networks with on-chip backpropagation trainings, where they do classification entirely on optic chip. And the second one instead is neuromorphic photonic computing with an electro-optic analog memory, where they do MNIST. So I was just wondering if you have any other cases. I have another one from MIT that maybe I can talk about later. But
so I go to a lot of sort of weird conferences on the edge of neuromorphic computing that are going more into the physics domain. And one of the things that always frustrates me at these conferences is that people say, oh, we can do MNIST, we can do this, we can do that. And my question is, why? Right? Do you have a path to being 100 times more successful at doing this and lower power, whatever it is, what is it you're selling, right? And if it's just, oh, look, I can do something that everybody else can do, and that means that I can do intelligent photonics, well, great, but don't call the investors. But if you have a path, if you have an argument as to why there are applications that in principle will be made possible once you push that technology further, then I'm listening. And that's the thing that I think can be missing in this space. And I'm not accusing Patty of that. I'm just saying in general, in that physics space, it's like, why do I want to do it your way if I can already do it the conventional way?
So I'm going to just add some information from that paper, and then I let Ralph fighting with you. So that specific paper is showing that they integrated analog memory into neuromorphic photonic architectures. They achieved 26 times power savings compared to conventional digit architectures, and they have still above 90% inference accuracy. And please, Ralph, take the floor.
Can I ask a question about that? I just heard you say, and as a journalist, right, this is something I'm always looking out for, compared to conventional digital architectures. So what I would say is, so you've got something photonic, which is inherently going to be a real pain in the ass to make it work. Comparing itself with the bog standard, whatever is available, whatever you can buy off the shelf, you should not be comparing yourself with that. You should be comparing yourself with the other emerging technologies. So I would say if they're not comparing themselves with neuromorphic technology, right? So what can analog neuromorphic do? What can digital neuromorphic do? If they're comparing themselves with conventional, then I'm rolling my eyes at this point. I'm sorry.
Maybe I can try to give another example. So, for example, MIT did a photonic processor that could streamline 6G wireless signal processing. So they built a photonic chip that classifies wireless signals running 100 times faster than the digital alternatives in 120 nanoseconds. So this is another application that could be interesting.
I want to just say that's a really good example. And I think it's a perfect example of what I've been saying all along, is that it's a communications example, right?
Yeah.
But at the same time, I would say that the argument that you're placing at the very beginning is the device argument, right? You're saying, hey, look, I've come up with a brand new device that has the ability to do compute as well as comms with photons, right? That is where I would start from. And then I would say, here is an example of a compute. It might be as simple as an XOR function, right? Which is a classical separation. And there's a paper actually in Nature Photonics that does exactly that. Just two classes separated, figure out how to make the entire process optical and compute and do a segmentation problem, right? That is just to say that we have the devices that can do it. What you do with those devices is what Giulia is referring to, saying, oh yeah, these are real world problem that I'm going to apply it to. We cannot go immediately to the large application space, right? We have to build things incrementally.
Okay, I need to stop you. Thank you so much, guys. Thank you again, Sunny, for this interesting interview, and Ralph for your great comments as usual. In the next episode, Sunny will talk to Dr. Jeff Scheinlein, founder of Great Sky in Boulder, Colorado. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Dr. Patty Stabile. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript, along with direct links to the other stories we've mentioned and other resources. Thanks for listening.